Hi everyone, welcome back to the workshop, and today I've got a Fluke 8846A 6.5 digit multimeter for repair. Now at the moment I've got it powered up, and as you can see I've got it in DCV mode and it's reading quite accurately. I've got my PDVS2 Mini set to 1 volt and wow, look at that, it's absolutely spot on. But the meter does have a problem. So let me just set up the multimeter and show you what the problem is. The problem is actually with its resistance mode, the ohms mode on the front of the meter. Now I've got it set up here with my resistance box. It's not particularly accurate, but accurate enough. And I've got it set to 0 ohms. And you can see, well, yes, we've got round about 0 ohms there. Maybe reading slightly high. But let me just dial up 100 ohms, and I'm in auto ranging mode at the moment. There's 100 ohms, a little bit off. So let me just try 1k, and we're miles off, almost half of what it should be reading. And it doesn't stop there. If I go to 2k, it goes up to 0.77, 3k, 0.8. Well, let's try 10k, and it's reading 1k. So it's all over the place. Now, if you didn't know, the way a multimeter's resistance mode works, the way it can calculate what the resistance is that you've got applied to the multimeter, is the multimeter will send out a constant current through your resistor and back into the meter, and then it simply measures the voltage across your resistor. And then Ohm's law, R equals V over I, it can calculate what to display on the front of the meter there. Now either there's a problem further downstream with the A to D, something like that, but I don't think so, because the DCV mode worked perfectly accurately. So chances are there might be a problem with the constant current coming out of the meter through your external resistor. Now it will also depend on what range you're on, because the constant current will change. It will apply differently to different ranges depending on what range you've got set on the meter. For lower resistance ranges, it's going to send out a higher constant current, and for higher resistance ranges, it's going to send out a lower constant current. So let me put an ammeter in series with this 2 connections here, and let's just see what sort of current we're getting. Now, I should mention before I start, there is actually nothing wrong with the meter's display here. It just happens to still have the membrane across the front of the meter. It's not my meter, so I don't really want to touch that. Just in case you wondered why it's a little speckled looking. So first things first, let's dial up a manual range. Let's go to 1k ohm range, and I'll apply 1k resistance. There we go. And you can see I'm getting about 0.586 milliamps through the external resistor. But if I drop that down to 0.7k, this current here is changing, and it shouldn't be doing that. And I think that's why this is starting to read wrong. And if I keep on dropping it down, let's go to 600 ohms, 0.7, let's go to 500 ohms, still 0.7, 400 ohms, 0.8. Yep, it's totally unreliable, that current, that constant current coming out through here. Now just as an example, I did the same with my R6581T, and in the 10 ohm range, irrespective of what resistance you applied, it was always outputting 10 milliamps. 100 ohm range, 10 milliamps, and then it dropped down to 1 milliamp for the 1k range, and so on right across the full range of the meter. Well, that's not what's happening here. So I think there's a problem with the constant current supply in the meter. So let's open it up and take a look inside. And there we are inside the unit. As you can see, one large PCB transformer on the side there. Looks like we've got a battery for the calibration. I'll have to be careful with that. Looks like we've got sensitive front end stuff underneath this little plate here, and a bunch of power supply stuff down here, a few electrolytic capacitors, and I wonder if that's the rest of the power supply circuitry down there. Now I don't have a service manual or any circuit diagrams for this here. I did contact Fluke begging them for the diagrams, but of course they were never going to supply it. So we're going to have to wing this repair, so we'll just see how we get on. And taking a quick look across the board, I'm not really seeing anything that's jumping out at me. I don't see any blown caps, any leaking caps. I don't see any blown resistors or FETs or ICs or anything like that. It looks pretty clean to me. Now interestingly, the user manual for the 8846A does actually specify the source current for the various different ranges. You can see that on the 10 ohm range it will output 5 milliamps with a compliance voltage of 13 volts, meaning it can output up to 13 volts to try to measure anything up to 10 ohms. And of course you've got the same for all the other ranges there. 5 milliamps, 1 milliamp, 1 milliamp, 100 microamps, and so on, all the way down to 1 microamp for the 1 gig range. And we are getting nothing like those values there, as we saw. So now that we have this information about the compliance voltage, I should be able to measure that on the multimeter. So with no resistor connected to the meter, that compliance voltage should appear at its maximum across the high and low inputs there. Now on the 10 ohm range, the manual said 5 milliamps, 13 volts. So we should be getting, well, I'm on 10 ohm range now, I should be getting 13 volts there. Oh, wrong way around. And I'm only getting 1.78. So that compliance voltage is way too low. But how about some of the other ranges? Well, the 1K range should be getting 6 volts. And in the 100K range, so you'd be up to 13 volts again. So let's try those. So let's try the 1K range. There we go. And measure that. 1.15. Wow. And the 100K range, yep, that should be 13 volts. I'm only getting 0.8. No much wonder the values are reading way too low. Well, I've decided to take the board out. I want to have a look underneath this shield here and see what's going on. So I've got the front panel off, just a couple of screws and a plastic clip to remove, and it basically just comes right off with the edge connector here. Nice modular format. Okay, so in order to try and fix this problem, I've actually had to do a little bit of reverse engineering. I did contact Fluke here in the UK, 2 different departments, and I got swapped between the 2 of them, and eventually they, as suspected, they would not release the schematics for this unit. And in fact, I did actually ask them, well, if you can't do that, any chance I can get a bill of materials so that I can see what components what? Because some of the SMD codes on top of some of the SOT23 packages, etc., are pretty hard to read. But of course, they said no to that also. So I had no choice but to try and work through the problem and try and do a little bit of reverse engineering, and I'll just show you what I found. So in ohms mode, manual range, in the 10 ohm range, I'm supposed to get 13 volts compliance voltage for the 5 milliamp source current. And then in the next range up, 100 ohm, it's a 6 volt compliance voltage for the 1 milliamp source current. So it's very easy for me to just switch back and forward whilst probing the PCB in order to try and track down the problem. Now I did manage to trace back to a couple of test points. TP10, which is here, and TP7 over there. And they're supposed to modulate when you change from 13 volts to 6 volts compliance voltage. And the reason I know that is, let me just zoom out, I do actually have another 8846A. Now this one isn't a working one, it's a faulty one also, but it's got a completely different fault. Now I did do a video 3 years ago, you can look it up on my channel, where I did take a look at both of these multimeters to try and do a quick repair. But it wasn't possible. The only step forward I made in that video was this meter here had a blown chip in it, so it didn't even power up at all. It was pulling the power supply down, something like that. 3 years ago, I don't quite remember. But I got it to the stage where it did actually power up, but I was left with overload. This one here, I never made a step forward at all in terms of the ohms mode not working. So when it came to looking at these two multimeters again, I'd elected to try this one first, the one with the ohms mode problem. I'll take a look at this other one in another video. I want to concentrate on this one. But the positive side is I can use this one for some tests on the circuit board, measuring some voltages just to see how they differ from this one here. Especially whilst using up and down buttons there to change that compliance voltage, irrespective of whether it just sits at overload all the time. However, it's not made all the easier, as I mentioned earlier, the fact we don't have schematics for this unit, and there is a lot of dual diode or NPN or PNP SOT23s scattered all over the board, especially around the range selection from what I can see. So I had no choice but to try and do a little bit of reverse engineering. Now like I said, I did start with that TP10 and TP7 and I worked backwards from there. And here's one of the schematics I've drawn up. The one thing I noticed on the board was also that there's an op-amp on the board, U30, and its supply pins are supposed to modulate also depending on what the compliance voltage is. And those supply pins on that op-amp weren't modulating either. So I kind of thought the two problems were actually related. So you can see I reversed engineered part of the circuit, which is on the underside of the board, and this is it here. So the op-amp here controls these two lines here. In actual fact, it controls its own supply pins. So I knew the problem must be upstream of this op-amp. And there's that same U30 op-amp there, and you can see how it's driven. It's actually driven from another couple of op-amps which I haven't reverse engineered fully. A couple of resistors come together and drive the negative input. I think it's in a voltage follower mode, driving further downstream. I managed to compare the circuits on both of the actual multimeters and found out that this pin here, pin 7 here, is driven by some pulses, a square wave of sorts. Now on the working unit, the waveforms do look a little bit different. They're a lot shorter on the working unit. So I figured the problem must be upstream of this also, because all the other voltages and signals on the input side look the same. So the problem must be upstream of this here. And I did a little table of the good versus the bad, as you can see there. And that's where I ended up across to the other side of the circuit board, where there's a differential analog multiplexer IC and a couple of SOT23 devices. And comparing both multimeters, I detected a problem on the drain of this MOSFET. So let me just show you on the scope. So first of all, measuring the working unit, if I just adjust the range and select the 10 and the 100 ohm ranges, so on the 10 ohm at the moment, just go to the 100 ohm, you can see it drops down in voltage. Back up again, back down again, and that's just me flipping between the 10 ohm and the 100 ohm ranges on the meter front panel. But compare that to the non-working unit, and I'll just flip between the ranges. You can see that it only changes by a few millivolts really. So I then probed around with my meter with the power off, and there's an SOT23 device right next to it. I think it's another transistor, and across two of the pins I'm getting about 190 ohms, but on the working unit that's way above 33k, something like that. So I think there's a problem with that transistor or somewhere else in the circuit that's causing it to have that resistance across the two pins. So what I need to do is just remove that transistor temporarily, and let's see what happens. So there it is there, removed from there. So now I can get my multimeter on those two pads and also the two pins of the device, and let's just see where we're getting 200 ohms on. So first of all, across the two pads on the circuit board, 18 mega ohm, wow. And the device itself, look at that. Definitely a low resistance there, just a bit hard to get onto the two pins without it moving around. Yeah, that's definitely looking like a problem device. Now the SMD code for that device is 26, and there's a few 26s, but I think I found the one that we've got here, and this is it here. It's a DTC144ECA, and it's actually a digital NPN transistor. Now what's a digital transistor as opposed to a normal one? Well, you can see down in the schematic here, it's actually just a normal NPN transistor of sorts, but it's got a couple of bias resistors built into it in order that it can act just like an inverter here. You've got an in and out effectively on your collector, and your emitter, you just use that as your ground. And thankfully, on page 2 of the datasheet, you can see that the input resistance R1 is specified at 47k. So to get anything like 200 ohms, because where I was measuring is across these two pins here, pins 1 and pin 2, well that's your input and ground. And you can see there's no way I should be getting 200 ohms between input and ground. And because the two resistors I think are both the same size, we should actually be getting about 100k, something like that. But the effect of this transistor in the circuit will actually affect that, but certainly nothing like 200 ohms. R1 stops that. So I need to replace that transistor. Now we'll actually replace that transistor with the right type, but I think for testing purposes I might get away with just fitting a normal NPN transistor and a couple of resistors. So let me do that and we'll see what happens. Right, as you can see, I've hacked on a small NPN transistor and a couple of resistors just to give it a go. No idea if that'll work. I didn't really look up too closely the spec of that digital transistor, but thinking this might work, it's worth a try. Right, it's powered up, so let me go on to the point that I was probing before, which I could see it modulating. And no, if you can see the scope there, it's only changing by a tiny little bit, so it's still not working. Well, looking a little bit closer at the circuit, there is actually an FET driving the input of that digital transistor there, a BSS 84, so I've got plenty of them in stock, so I think I'll just change that out just to see if it makes any difference. If not, I'll have to reverse engineer this whole circuit. Okay, so I've done a little reverse engineering around the digital transistor there, and that FET I replaced to replace those two there, and just to see what was going on. Now this is not perfect and it's not complete, but it gives me a little idea of how to proceed. Now we've got a multiplexer at the top. This is a differential multiplexer, so it's got a DA and a DB output. Don't really care about the inputs at the moment, but the signals coming out on DA and DB match both the faulty unit and the working unit when I change ranges. So I'm quite happy that we're getting the right signal to the source of this FET and also to the gate. Now there's probably some more lines here that I've not included here. This isn't quite right, I don't think, but this is what I've got so far. And the gate of this FET is driven by this op-amp here. Now pin 7, I'm getting the same signal on the working unit and the faulty unit. And bearing in mind I've replaced the FET and I've made up my own digital transistor, this is the line here that is not switching properly. And all it does is goes away down here into this voltage follower. Now from what I can see so far, the only way that this line can be pulled low and not switched properly when I change ranges is if this voltage follower is somehow pulling it down. Ah, we're getting somewhere now. When I reverse engineered this section of the diagram, I'd missed off this section here. And what you've got is a small inductor and a couple of back-to-back diodes in an SOT23 package. However, there's a problem with this section here, because this line here will be as high as 13 volts and down as low as 3 volts depending on the range selected. And there's no way you could have 13 volts, 3 volts, even 2 volts across this forward bias diode here, down to ground. And then I realised this line here is shorted down to ground on the board and it's not supposed to be. There's a problem on the back of the board. It doesn't look like this. So let me just update this diagram and I'll show you what it really looks like. And there it is. What we've got is a small SOT23 package on the rear of the board, 2 Schottky diodes, and this one here was dead short. So I was getting this line here down to ground, and that was pulling down that line there. So I've removed that package from the board and I've no longer got a short. So it's definitely faulty. It's a BAT54S. So I'll just go away and fit a new one and then we'll try it out. So there we are on the back of the board. That's the signal diodes there, and that's the Schottky diodes. Now I don't have a dual package SOT23, so I've got one in order, but just for the time being I've hooked up a couple of individual Schottky diodes and fitted them just enough room to squeeze them in. So let's prepare for a power up and see if we've fixed the problem. Right, I've got power up. And what I want to see is the drain on the P-type varying when I change the ranges on the front of the meter. Okay, let me just get it in ohms mode. There we go. Right down to the 10 ohm range. And let's just scope that drain. And I'll just go up 1 on the range. Yes! Look at that! Back down again. Yes! That was the problem. Schottky diode. Brilliant. But am I getting the compliance voltage? Well, I've got my meter here, so let's measure it and see what we get. Right, let me just stick the multimeter probes in the banana sockets here. Yes! 13 volts. Brilliant. And it should vary. I think, was it 6 volts it goes down to? I can't remember now. When I go to the next range up. Yes! Brilliant. So the compliance voltage is now working. Brilliant. But is it accurate on the front of the meter when I stick in a resistor? Well, we'll try that now. Right, so I'm on the 10 ohm range. So let's try 10 ohms. Now this resistance box I know is really inaccurate. It's quite old. But whether it's that far out, I can't remember. We'll try it out on this meter in a second. So let's try the next range up, which is 100 ohm. So let's try 100 ohm. Yes, that's quite high. And then the 1K range. Yep. And then the 10K range. It should be okay as well. No! That's reading overload. Let's try 1K in that range. Wow! That's reading miles out in that 10k range, but the compliance voltage was okay. So we've still got a problem. Let me just double check the compliance voltage again. And I'm on, that's 10k range, 6 volts. That's what I should be getting, and it should be able to source 100 microamps. So let me just put in the resistor again. Let's dial up 10k. And let's see what that compliance voltage, or the voltage, has dropped to now. Yeah, 2.1 volts. Well, that's it measuring across the resistor. So it's bound to drop. But looks like we've still got a problem. So let's try the resistance box into the 786. So I've got it set to 1k. Is it really that far out? No, it's not too bad. Let's try 100 ohms. Yeah, a little bit out there. And the 10k. Yep, 10k. Yep, so definitely we've still got a problem with the meter. Well, so what's next? Well, I've got my dual Schottky here, and I've got that digital transistor from Farnell and RS. So I'm going to fit them and then just see if the same problem exists after I replace these two. Right, let's put the digital transistor in place, if I can manage. There we go, it's good enough. Perfect. Well, let's turn over the board and do the dual MOSFET now. And there we go. So I think we can now try for a power up again, and let's see if the same problem exists. But before I try a resistor, I do actually want to check that we're getting the compliance voltage. So I'll just power up. And I'll put it right down to the bottom range. And we should be getting 13 volts. Yep, we do. Back to front, but never mind. Yep, we've got 13 volts exactly. So let's apply a resistance and just check and see where we are now. Okay. So let's bump it up to the 1k range. There, and I'll dial up 1k. And we're getting 1.1, so that's still high. So let's go up to the 10k range and dial up 10k. And that's overload again. So let me just take that down to 1k again in the 10k range. And we're still getting 2.6k or thereabouts. So we've still got a problem with the multimeter. Okay, I found the issue why it's reading high, or the symptom anyway. I've got 1k resistor hooked up. I'm measuring the current through that resistor, and I'm in the 10k mode, and according to the specifications, the meter should be sourcing 100 microamps across that 10k range, but I'm measuring 266 microamps. Now if you do the maths, with that increase in current, I'm going to get more voltage across the resistor or the terminals on the multimeter. Now the meter's burden voltage will have a slight effect, and if you do the maths, I'm getting 2.9k on the reading. Well, that's entirely consistent with the voltage of 0.29 volts across the terminals with the 267 microamps. So no wonder it's displaying that value. It's a factor of 2.6 to 2.9 depending on the burden voltage times too big. Hence, instead of 1k, it's reading 2.9k. So I've got to track down why we're getting too high a current out of the terminals. on that 10k mode. I think all the other modes, all the other ranges have exactly the same problem. It's just very apparent on the 10k range. So I need to track that down. Now this is where the other multimeter is not going to help me, because I think it has a similar problem, and that's why it's reading overload on the display. So it looks like I've got more reverse engineering to do. Well, I've just finished a little bit more reverse engineering round about the comparator here on that section that had done some reverse engineering already, and I've kind of detailed that up on here, and it kind of ties into one of the other drawings that I've done. I've redrawn this one here, made some improvements, some better tie-ins. The comparator ties into the analog switch circuit there, and to tell you the truth, I'm not getting anywhere. I've got 10 sheets here of reverse engineering, some point-to-point drawings, some schematic redraws that I've done, and really I don't think I'm getting anywhere. This circuit board has got so many components on it, so many SOT23, just look at them here. Even round about the voltage reference you've got a bank of 8 and another 2, and they're just scattered all over the place. And including the back of the board as well, you've got SOT23s everywhere. And being a multi-layer board, it's just a nightmare to try and trace anything. So, yep, you can maybe hear it in my voice, but I think I'm going to give up. Yep, I'm going to give up repairing this 8846A for the second time. I gave up 3 years ago, although I did put much more effort in this time to try and get it up and running. You know, I did find a blown Schottky diode, as you saw earlier in this video, and a dodgy digital transistor, and that did improve this area here. I got that partially working, and I haven't even found a link between this area here down into this area here yet, which there obviously must be. So like I said, I think I'm going to give up for the second time. But what I will do is I'll put all my reverse engineering drawings in the video's description down below. I'll scan them all in, warts and all, and maybe it might be useful for somebody else. Maybe somebody else has done some other reverse engineering in different parts of the circuit. Now I did contact Tektronix because there is a DMM 4050 which is identical to this unit here. And Tektronix just referred me to Fluke because Fluke were the people that designed this in the first place. So even though there is a Tektronix branded unit, they don't have the schematics, or at least that's what they're telling me. But I do thank Tektronix and Fluke for getting back to me relatively quickly, even though it wasn't good news. Now as for the other unit, through the course of repairing this unit, I did actually find a faulty Zener diode on this unit here. And there it is there, it's an SOT23 device, and it was more or less short circuit, so I just replaced it with a normal through-hole 5.1 volt Zener, and it just actually happened to be in that same section of board that I'd already reverse engineered, so it was relatively easy to find. But it didn't bring this unit back to life. It still says overload on the display, so there's obviously a problem somewhere else. Now I think the two faults with both units are very, very similar. I'm actually not going to try my hand on this unit here. So for the time being, I think I'm going to call it a day with these units. I'll put them back on the shelf, and you never know, I might have another go in the future. Definitely if I can find schematic diagrams or any partial reverse engineering that maybe somebody else has done. But for the moment, they go back in the shelf. Thanks for watching.